Hello, this video is going to be a bit of a departure from kind of videos I usually do with all camera test footage and that. Over the last 2 or 3 years I've been teaching myself electronics. It started with me just trying to learn enough to repair some old video recorders and cameras, and then I started building little circuits from designs that I got off the internet for different things like guitar distortions and power amplifiers, like little ones and that. I made a little guitar amp that I built in back of an old speaker, kind of like the DK amp that Brian May uses. I got quite interested in audio circuits and I started reading a lot of stuff. Some books by Bob Cordell, Doug Self, Randy Sloan, and just things off the internet, and watching videos and learning about how amplifiers work. And I've got to a point now where I've started designing things myself, which is what this video is about. If you couldn't tell by looking at it, then you probably worked out from what I've said that this is an amplifier, specifically an audio power amp. I've designed it myself and built it on this prototype board. It uses a fairly standard topology. It's got an input stage, which is that. This voltage amplifier stage, which is this bit, and an output stage. I'll include that in there. The input stage is uses a circuit called a differential pair or long tail pair. The main job of the input stage is to correct errors introduced by the rest of the amp. Voltage amplifier, surprisingly enough, amplifies the voltage. It's used in a configuration called a common emitter. It provides all voltage gain for the amplifier, so the signal at this point coming out of here is of the same amplitude as what reaches the speakers, basically, but it's high impedance, so you can't drive a load like a speaker properly. So we have this output stage. The output stage is a unity gain buffer, which means it doesn't have any voltage gain, but it provides current gain and low output impedance that you need to drive speakers. It uses what's called a complementary feedback pair. It uses two of them, or a Zickley pair. Zickley pair, I'm not sure how you pronounce it, which is that circuit. There is two transistors connected in such a way it makes a sort of super transistor with like the gain of the two multiplied together. It's a class B output stage, which means that each of these pairs, like that's one, each one of these only conducts on half a waveform. So say you've got a waveform like that, that's 0. As it comes as it goes positive, this pair conducts, and as it crosses over 0 into negative, that pair turns off and this pair conducts, and that one turns off. Now a transistor, and including these super transistors, they need a voltage of about 650 millivolts or thereabouts between the base and the emitter before they'll start conducting. And so with this output stage, with the upper and lower transistor pairs, that's about 1.3 volts in the middle, so like from there to there, where both will be turned off, because that's turned off at 0.6, right down to 0 it's off, and then till it gets to minus 0.6, 0.65, that's when that one starts conducting. So you've got this dead area, so you end up with a waveform that looks like that. So you basically need to set them up so that you've got this voltage between base and emitter already, so that when the signal goes positive, this one's already just sort of starting to turn on, so it immediately conducts, and as it gets down to 0, that one's already turned on and it conducts, that's where this part of the circuit comes in. This is called a bias spreader, or a VBE multiplier. So how this works is, it's again because of this 650 millivolt between base and emitter, you've got this 650 millivolt across these resistors, and so when you put a voltage across a resistor, you get a current flowing through the resistor. The voltage over resistance equals current, Ohm's law. Because this is a series circuit, you've set your current flowing in here. It's a series circuit, so the same current's got to flow in this resistor, and so you've got current flowing through it. A voltage develops across it by Ohm's law again. And what you have to do is set these resistors so that you've got just enough voltage between here, going into the base of this transistor, and here, going into the base of this one, to have these both just turning on when it signals at 0 volts. Yeah, this resistor here is set is use a potentiometer, so you can set it correctly. This is the output. That's representing a speaker. That's a Zobel network that's used to stabilise what load the amplifier sees. But you've got this feeding back from the output. You've got this circuit here, which is a voltage divider, and this sets the gain of the amplifier, and it's by this connection that your input stage works in terms of correcting your errors by a process called negative feedback. What this circuit does is it always tries to keep voltage at each of its inputs, this and this, the same. And the way it does that is by altering its output. So say at a given instant you've got the input signal coming from here. This is just represents your input signal. Say that's at 1 volt, this circuit will put out whatever it needs to make the voltage here 1 volt, and because you've got this voltage divider that's dividing the signal by 19, the output signal by 19, that means the voltage at the output of the amplifier is going to be 19 volts when you've got 1 volt here. So this negative feedback system, it lets you set the gain by just using these two resistors, rather than relying on characteristics of the transistors that you're using. And it also gets rid of distortion by making sure that what's at the output is just exactly what's at the input, but multiplied by the gain that's set by this voltage divider. In this case, I'll say it's 19. There's actually a component on the amplifier itself that's not on this schematic, and that's because I added it later, when I'd tested amplifier, and I added it because I found that I were getting oscillation on the top half of the sine wave. I was doing it with sine wave testing, so rather than a nice clean sine wave like that, at the top of the sine wave it was fuzzy like that. What can happen with this type of output stage is that, because as well as this global negative feedback that you've got through the whole circuit, you've got local negative feedback in these output stages, and you can get phase shift, and when that gets to 180 degrees, if there's still gain at that frequency, then your negative feedback turns into positive feedback and you get oscillation. So what I did was I put a capacitor here, and so as frequency increases, it rolls off the gain. And you've got the same mechanism here. To do that for the feedback loop, the entire global feedback loop, to keep that stable, so that by the time, because you get parasitic capacitances, and there's capacitance in transistors and in your traces and stuff, and it all kind of adds up. Each bit of capacitance adds a bit of phase shift, and as it gets like that, it's like a kind of in the time domain, it's like a delay to the signal getting to the next point, because you've got to charge and discharge this capacitance. So as frequency gets higher, that delay constitutes more of the sine wave, or whatever wave it happens to be. So you get to a point where, rather than feeding this back to your amplifier to here, you're going to be feeding that, so rather than it subtracting, it's adding. But anyway, that's the amplifier. I mean, this topology is it's like really common. It's nothing like that I've come up with or anything. It's, if you look inside an amplifier, or you look at a schematic for an amplifier, most amplifiers will have some sort of variation of this general circuit. I mean, there'll be be differences, and there'll be more complexity, because you'll have protection circuitry, which I haven't got in this, to protect your output stage, and from difficult loads and things, which I've not got that in this amplifier. But there will be somewhat along these lines generally for a normal like linear amplifier. So what I thought I would do is test it out. I mean, I've tested it myself, but we'll see what sort of power we can get out of it. We'll do some tests, see at what point it clips and how it performs into an 8 ohm load and a 4 ohm load. I've got my preamp here, my homemade preamp I built. Just connect it up with no load at first and see what we get. What I'm going to do is play a 1 kHz sine wave into it and gradually increase the volume until we get clipping, and I roll it back and just see what, whereabouts, what level it clips at, and we'll be able to work out what power we're getting. At the minute it's not driving a load other than like the oscilloscope. So we'll see what it's like with that, and then I'll try an 8 ohm load. We're just starting to get clip in there. See it flying off. So we're getting like, and that's still clipping a bit. Yeah, it's just slightly. So we're getting 3 volts. Well, not 3 volts, 3 divisions. It's 5 volts per division. We're getting 15. Just about 15 and a half volts peak. Divide that by 1.414. It's 10.96 volts RMS. Right, so I'll connect a load and we'll see what we get with an 8 ohm load. Right, I've connected this load now, so we'll try it again and see what we get. It's an 8 ohm load. Getting clipping a bit earlier now, so we're getting about 12 and a half volts now. 12 and a half volt peak. 12 and a half divided by 1.414. 8.84 volts RMS. Square that is 78.14 divided by 8 is 9.76 watts RMS we're getting there for clipping. I ain't got anything to measure distortion or anything, which I mean that'd be good if I could do that, but I can't. It's just a basic and all that analog oscilloscope. There's no like Fourier analysis or all like that on it. So yeah, that's 9.768 watts. I'll try it with a 4 ohm load now and see what we get. So obviously as it's pulling current, I mean what happens is you get the rails sag a bit, they drop down. So it's just what happens with transformers. Oh wait. Right, I've got a 4 ohm load connected now. Let's see what it does into 4 ohms. So we're getting 10, about 14, about 10, 5, about 9 volts in there. But what is happening, we've got this a bulb tester, a light bulb in series with the circuit, and what's happening is that it's limiting it. That's like a safety measure for when you're testing things like that. You put a bulb in series with mains, and if it starts to pull a lot of current, the bulb will light up. I mean, it's not on full brightness obviously because it's not pulling. I mean, that's like a 60 watt bulb, I think. It's obviously it's not pulling 60 watts, but that'll be dropping rails. So what I could do with doing really is like testing it without that, and get a more true reading, or at least maybe putting an 100 watt bulb in or something, But I mean, this is what we're getting. I mean, with that 8 ohm load, that didn't come on, so I mean, I have to do another test without that in and see what happens. But what did I say? What 9 volts. So that's 10 watts again that we're getting. With that, so I think that is limiting it quite a bit, I'll put it back on the 8 ohm load and I'll test it at some different frequencies, see how it handles them. Alright, we're back on the 8 ohm load now. I'll put this sweep on it, starting with 20, 30, 40. I'll start it again. This is 20 Hz, 30, 40, 50, 60, 70, 80, 90, 100 Hz, 200, 300, 400, 500, 600, 700, 800, 900, 1000, 2000, 3000, 4, 5, 6, 7, 8, 9, 10, 15, 20, 30, and it's gone back to 20 now. It's back to 1 kilohertz, I should say. I'll put this sweep on it, starting with 20, 30, 40. I'll start it again. This is 20 hertz, 30, 40, 50, 60, 70, 80, 90, 100 hertz, 200, 300, 400, 500, 600, 700, 800, 900, 1000, 2000, 3000, 4, 5, 6, 7, 8, 9, 10, 15, 20, 30, 4, and it's gone back to 20 now. It's back to 1 kilohertz, I should say. I can actually hear it when it's at these high frequencies. You can actually like hear it through the thing. I don't know. I don't know if it's one of them capacitors. I don't know if you can hear it or not. Quite quiet. That means I can actually hear the noise coming out of the circuit. Like it might be this capacitor vibrating or something. You get a 20 kilohertz sine wave. That's 20 hertz, sorry. See, I mean, there's no move on one. Not getting any change in frequency response. It's not, it's not going down. So ours got a flat response. That's 1 kilohertz. Yes. Kilohertz. It's pretty flat. I've got some square waves on here, but I don't think, I'm playing it through my phone, I don't think the phone will actually put out a proper square wave. So I'm try this 1 kHz square wave. Yeah, that's not the amplifier doing that, it's the phone. Turn it up to clipping, that's what you get. I could do with something that's quite a proper square wave so I can test it with that, because they're hardest kind of waves for them to do. That's about it really. Thanks for watching. Okay. Right, I've decided to remove that bulb limiter and do some tests to see what power we can actually get at 4 ohms without that limiter in place. Okay, so I've got it set up with a 4 ohm load now, and we'll see what happens. And it's clipping at top before it clips at bottom. Whether that's a preamp, if it's like loading preamp too much, I don't know. It should really clip evenly, but these output transistors are getting hotter than they were before. Let's level that up to middle again. Yeah. I can hear the amp something in amp sort of resonating. If it's that capacitive, I don't know. So getting to 11, 12. So we're getting about 12.5 volts. Turn that off. So what's that? 4.5 divided by 1.414. 8.84 volts RMS. Square that. Divide by 4. 19.5 watts we're getting. This is this transformer's it's 12 volt transformer I'm using. We're getting 19.5 watts into 4 ohms there.